December 5th, 1944. A cramped conference room aboard the USS Enterprise, somewhere in the vast expanse of the Pacific Ocean. The aircraft carrier, scarred but unbroken from numerous engagements, housed the nerve center of naval intelligence operations, where two of the Navy's most accomplished analysts were about to confront a truth that would shatter every assumption the Japanese military held about American naval defenses. Commander Richard Harlow, head of Naval Weapons Assessment, sat across from his counterpart, Commander Thomas Westfield, who led Technical Intelligence Division. Both men had reached their positions through demonstrated analytical brilliance and meticulous attention to detail. Both had spent years tracking enemy capabilities with professional precision, and both were now examining reports that represented something far more devastating than any conventional naval victory. Before we jump back in, tell us where you're tuning in from, and if this story touches you, make sure you're subscribed because tomorrow I've saved something extra special for you. Between them lay a stack of papers that appeared unremarkable, standard battle damage assessments captured during recent engagements in the Philippines. The forms were bureaucratic, mundane, filled with columns of numbers recording hits and misses, ammunition expended, and aircraft downed. Nothing about their appearance suggested they contained information that would prove the technological impossibility of successful kamikaze attacks against the American fleet. Yet the numbers they contained represented a technological reality so overwhelming that both officers had spent the previous week cross-referencing sources, checking calculations, and searching desperately for errors that would make the figures less apocalyptic. Westfield's hands trembled slightly as he pushed the top document across the desk. It was a simple damage assessment form from the destroyer USS England, listing kamikazes engaged and destroyed during a single afternoon of combat operations. The form was stamped, dated, signed by multiple gunnery officers, clearly authentic. Harlow studied the figures in silence, his face growing pale as he absorbed their implications. The American 5-inch guns with the new VT fuses were destroying kamikazes at ranges, and with accuracy that conventional fuse technology had never achieved. He looked up at Westfield, searching his colleague's face for some indication this was error or deception. Westfield's expression offered no comfort. He had already worked through the same calculations, reached the same conclusions, and spent 3 sleepless nights hoping he was wrong. "This cannot be accurate," Harlow said quietly, though his tone carried no conviction. He was not stating a belief, but expressing a wish, the desperate hope that reality might somehow be less terrible than the evidence suggested. Westfield pulled another document from the stack. "I thought the same. This is a gunnery report for the USS South Dakota, covering a single engagement lasting just 48 minutes. They destroyed 19 attacking aircraft. With conventional time Fuzes, they would have been lucky to hit 3. He paused, letting the numbers settle. "I compared this to our own air defense capabilities. An entire Japanese carrier battle group with dozens of anti-aircraft guns achieves fewer aerial kills in an entire day than this single American ship managed in less than an hour." The two men had spent the past week engaged in exactly this kind of comparison, cross-referencing American battle reports with Japanese defense capabilities, interrogations with aerial reconnaissance data, agent reports from neutral countries with analysis of captured equipment. Every source confirmed the same impossible truth. America was not just outproducing Japan, they had developed a technological breakthrough that defied comprehension, that made Japanese air attack tactics look suicidal by comparison. The numbers told a story that no amount of courage, tactical brilliance, or ideological fervor could overcome. Japan was fighting against electronic wizardry itself, and electronics always wins. The journey to this moment of terrible clarity had begun months earlier, but its roots stretched back years into fundamental miscalculations about American technological capabilities. The Japanese intelligence services had tracked Allied weapons development since before the war, compiling reports on research facilities, laboratory capabilities, and resource availability, but they had consistently catastrophically underestimated what America could achieve when fully mobilized. This was not mere incompetence. The assumptions built into Japanese strategic thinking, shaped by their own technological experience, made American electronic innovations seem impossible, even fantastical. Japan's own wartime experience colored everything they believed about anti-aircraft defense. By 1944, the empire had mobilized every available resource, stripped occupied territories of raw materials and skilled labor, and pushed its technological capacity to what seemed like absolute limits. Japanese factories operated around the clock. Workers put in extended shifts. Production of weapons and ammunition had increased dramatically from pre-war levels. Japan was producing aircraft, ships, and artillery at rates that would have seemed unthinkable in 1939. Yet, despite this total mobilization, despite conquering much of East Asia and exploiting its resources, despite the desperate intensification of production under military direction, Japan was losing the technological war. The fundamental Japanese miscalculation began before the first shot was fired at Pearl Harbor. In early 1942, American scientists at the Johns Hopkins Applied Physics Laboratory had achieved a breakthrough in proximity fuse technology. The VT, variable time, fuse contained a miniature radio transmitter and receiver that detected when it was near a target and detonated the shell at the optimal moment without requiring direct hits. These developments were detected by Japanese intelligence through multiple channels. When presented to Imperial Navy leadership, their response was dismissive, even contemptuous. The reports were obviously American propaganda, they concluded, designed to intimidate Japan and boost Allied morale. The assessment seemed entirely reasonable based on available data. In 1941, American anti-aircraft technology relied on mechanical time fuzzes that required precise calculation of altitude, speed, and trajectory, APAs, all nearly impossible against maneuvering aircraft. Japanese pilots routinely avoided or survived anti-aircraft barrages through evasive action. American naval guns, while substantial in number, were focused on surface targets rather than air defense. How could a nation suddenly develop miniaturized radio equipment reliable enough to function after being fired from a naval gun? It violated every principle of electronics development that Japanese experience had established. Building such devices took years of careful research. Miniaturizing radio components required breakthroughs in multiple fields. Manufacturing such precision devices demanded techniques beyond any nation's capabilities. The American announcement seemed like the fantasy of desperate engineers rather than achievable reality. Admiral Isoroku Yamamoto, architect of the Pearl Harbor attack and one of Japan's most forward-thinking naval officers, reportedly dismissed the reports when he heard of American proximity fuse development. While this account comes from secondary sources rather than contemporary Japanese documents, multiple historians cite Yamamoto, stating that Americans might mass-produce ships and planes, but precision electronics at this scale remains beyond anyone's capabilities. Whether the exact quote is accurate, the sentiment it captured was certainly real. Japanese leadership genuinely believed American electronic capacity was unsuited for mass-produced proximity fuses. This assessment seemed supported by observable facts. America excelled at producing automobiles, aircraft, and ships in massive numbers. But miniaturized electronic devices required different expertise, different manufacturing techniques, different quality control approaches. Japanese electronics had been developing for years. How could American consumer goods manufacturers possibly match Japanese precision electronics capacity? The Japanese failed to understand something fundamental about American scientific and manufacturing potential that would prove decisive. The United States had mobilized its immense scientific establishment, FEA, universities, research laboratories, and industrial R&D departments, TAC, toward military applications with unprecedented focus and funding. What looked like technical impossibility was actually enormous potential waiting to be activated. When American scientists tackled the proximity fuse challenge, they were not asking electronics manufacturers to build entirely new capability from nothing. They were asking them to redirect existing technical knowledge, apply assembly line techniques to electronics, manufacturing, and scale production in ways never before attempted. The technical foundation for revolution already existed, requiring only application rather than invention. Japan, by contrast, had no such capacity. By 1943, Japanese electronics research was already operating at near capacity. The imperial regime had been developing radar and communications technology since the 1930 seconds, steadily expanding electronic capabilities year after year. There was little unused scientific capacity to activate, few unemployed engineers to recruit, minimal laboratory space sitting idle. Japanese expansion could only come through building new research facilities from scratch, training new engineers, or capturing foreign technology. Each of these approaches took years to implement and faced inherent limitations. The fundamental difference in starting positions, PASS, American unused scientific capacity versus Japanese full utilization, PAS, meant that America could develop and scale up production of revolutionary technology far faster than Japan could match. The Japanese intelligence services, particularly the Naval Research Division under Commander Takashi Miyazaki, had the institutional responsibility for tracking Allied weapons development. Miyazaki came from a distinguished family of naval officers. His family had served Japan for generations, and he embodied the professional naval officer class, methodical, detail-oriented, committed to objective analysis. His organization collected information from multiple sources, including reconnaissance flights, signals intelligence from radio intercepts, agent networks operating in neutral countries, systematic interrogation of captured prisoners, and equipment captured during military operations. Throughout 1942 and 1943, as America refined the proximity fuse and began deploying it, the intelligence picture reaching Tokyo remained incomplete and confusing. Preparing and narrating this story took us a lot of time, so if you are enjoying it, subscribe to our channel, it means a lot to us. Now, back to the story. Reports of American anti-aircraft effectiveness varied wildly depending on source and method. Some indicated massive increases in hit probability, ships downing multiple aircraft in single engagements, unprecedented success rates. Other reports suggested continued technical struggles, fuses malfunctioning, systems plagued by reliability issues. The Japanese High Command chose to believe the more comforting assessments, the ones that aligned with their preconceptions about American technological limitations. This selective acceptance of intelligence was not unique to the Japanese. All military organizations tend to favor information, confirming existing beliefs over data challenging core assumptions, but in Japan's case, the cost of this cognitive bias would prove catastrophic. After all, Japan was winning in 1941 and early 1942. The Imperial Navy had destroyed much of the American Pacific Fleet at Pearl Harbor in hours. Japanese forces had conquered the Philippines in weeks, Malaya in 70 days, the Dutch East Indies in 3 months. Japanese forces occupied Korea, Manchuria, large portions of China, and much of Southeast Asia. The Imperial Navy had proven itself the most formidable naval force in the Pacific. Japanese aircraft and naval tactics were clearly superior to those of any opponent. Japanese pilots were sinking Allied shipping faster than it could be replaced, or so Tokyo believed. Why should Japanese leadership fear a nation that had suffered such humiliating defeats, whose navy was crippled, whose defenses seemed inadequate, whose technological capacity was oriented toward mass production rather than precision electronics? This comfortable certainty began developing cracks at the Battle of the Philippine Sea in June 1944, when Japanese naval air forces encountered American task forces equipped with the new VT-Fused 5-inch guns. Japanese commanders expected to overwhelm American defenses through sheer numbers and pilot skill, tactics that had worked effectively in earlier engagements. What they encountered was something else entirely. The Americans were indeed operating conventional guns and gun directors. That assessment proved accurate, but something about the American defense seemed impossibly, unnaturally effective. Wave after wave of Japanese aircraft fell from the sky, destroyed at ranges that seemed impossible with conventional fuses. American ships that should have been overwhelmed by multiple simultaneous attacks emerged unscathed, surrounded by burning aircraft and floating debris. The sheer effectiveness of American naval anti-aircraft fire was staggering and unprecedented. Japanese squadrons that launched, with high confidence in their attack plans, returned with catastrophic losses, some reduced to mere fragments of their original strength. The few pilots who survived reported shells exploding near their aircraft without direct hits, blasts occurring with uncanny timing, defensive fire that seemed to anticipate their evasive maneuvers. Vice Admiral Jizaburo Ozawa, commanding Japanese carrier forces during the battle, began sending increasingly alarmed reports to Tokyo. Each American ship, he noted, seemed capable of creating a virtual wall of explosive shells through which no aircraft could penetrate. American task forces operated coordinated defensive screens that made conventional air attack suicidal. Supply installations captured during earlier Japanese advances had shown no sign of this revolutionary technology. Ozawa, known for his tactical brilliance, understood that tactics became irrelevant when facing such massive technological superiority. He urged development of new attack methods, arguing that conventional approaches made defeat inevitable regardless of pilot skill or numerical advantage. These reports were noted, filed, and largely ignored by the high command in Tokyo. Ozawa was known for caution, for emphasizing difficulties over opportunities. His complaints were dismissed as the usual admiral's grumbling, the predictable tendency of field commanders to exaggerate enemy strength and minimize their own capabilities. Admiral Soemu Toyoda, commander-in-chief of the combined fleet, personally rejected Ozawa's assessments, insisting that pilot skill and spiritual strength would overcome technological advantages. Toyoda's worldview could not accommodate the possibility that American electronic ingenuity might matter more than Japanese fighting spirit or flying skill. But the intelligence analysts could not so easily dismiss what they were seeing. Throughout late 1944, as the war turned decisively against Japan on multiple fronts, the volume of concerned data increased exponentially. After the Battle of Leyte Gulf in October 1944, Japanese intelligence conducted systematic analysis of aircraft losses based on returning pilot reports and observations from support vessels. The debriefing teams, operating from questionnaires developed by the intelligence services, sought to understand not just tactical details of the fighting, but broader patterns of American anti-aircraft capability. The stories these survivors told were remarkably consistent across rank, unit, and experience level. Every debriefed pilot described American anti-aircraft fire that seemed guided by unseen hands. They spoke of shells exploding precisely as aircraft attempted evasive maneuvers. They described American guns firing fewer rounds but achieving more hits than should have been possible. They recounted seeing entire squadrons destroyed in minutes by defensive fire that previous experience suggested should have been survivable. Medical officers reported wounded pilots with unusual shrapnel patterns, consistent with proximity detonations rather than direct hits. Some accounts seemed so extreme that intelligence officers initially suspected exaggeration or Allied psychological warfare. But the consistency across hundreds of independent debriefings made dismissal impossible. Veteran naval officers, frontline pilots, squadron leaders, fleet commanders, SA, all told the same stories of American anti-aircraft fire that seemed guided by invisible hands. These accounts matched what Japanese forces were experiencing on other fronts. In the Philippines, captured in October through December 1944, Japanese air units encountered similar patterns. In Iwo Jima, where American forces would land in February 1945, the pattern repeated. Everywhere Japanese forces engaged Americans, they found enemies with seemingly supernatural defensive capabilities. These pilot accounts, while concerning, could theoretically be dismissed as subjective impressions exaggerated by defeated airmen trying to explain their failure. But then the captured technical documents began arriving in Tokyo in greater numbers, and these could not be dismissed. Unlike survivor accounts, technical manuals were clinical, bureaucratic, undeniable. They were not meant to impress or intimidate. They were simply the routine paperwork of American naval operations, the mundane guides that instructed sailors on using new equipment, and the technological specifications they contained were apocalyptic for Japanese strategic planning. One particular document proved especially illuminating: a maintenance manual for the Mark 32 VT fuse captured from a damaged American destroyer in late 1944. The manual, stamped and signed by multiple technical officers, detailed maintenance procedures and basic operating principles. Commander Miyazaki compared this to Japanese anti-aircraft technology. The Imperial Japanese Navy's best-time FARs required manual calculation of target altitude, speed, and trajectory, OPAR, then setting the fuse timer by hand before loading. The American VT fuse contained a miniature radio transmitter and receiver that automatically detonated when near a target. The disparity was not marginal. It was a difference of kind rather than degree. The ammunition figures in the same manual were even more devastating. American ships could sustain high rates of fire with these advanced shells. The manual indicated that a Fletcher-class destroyer carried approximately 600 VT-fused rounds as part of its standard ammunition load. Japanese destroyers carried perhaps 200 conventional time-fused anti-aircraft rounds during the same period, and those were considered adequate supply. The Americans were firing shells that were not just more effective per round, but they carried 3 times the ammunition supply and could afford to use it liberally. This was not some special preparation for a major battle where supplies were concentrated for a brief period. This was normal, an operating procedure, the routine ammunition load for regular operations. The implications were staggering. American naval guns could provide air defense at effectiveness rates that would exhaust Japanese air power in days, and they could maintain this indefinitely. The technical breakthrough of the VT fuse meant that Japanese air superiority, YOPD, the foundation of imperial strategy since before Pearl Harbor, had simply evaporated against this new technology. The reliability figures told an equally disturbing story. During early testing in 1942, the VT fuses had achieved a 50% reliability rate, HAA, already revolutionary compared to conventional time fuses. But by 1944, the manual indicated reliability rates exceeding 85%, meaning that nearly 9 out of 10 shells would function as designed. The Japanese Navy had never achieved reliability rates above 30% with its most advanced time fuses. The mathematical implications were inescapable. If American ships could defend themselves with this effectiveness rate, and they had dozens of task forces deployed across the Pacific, then conventional air attack had become obsolete overnight. Japanese naval strategy, built around carrier-based aviation, had become suicidal against such technology. Commander Miyazaki approached these documents with the methodical precision that had made him one of Japan's most respected intelligence officers. He was a naval officer from a family that embodied Japanese military tradition, but he was also a professional analyst trained to evaluate evidence objectively regardless of personal preferences. The captured American documents represented hard data that could be quantified, compared, and analyzed. He began calculating systematically. If one American task force could defend itself with this effectiveness, and the United States had deployed dozens of such task forces across the Pacific, then the total American defensive capability was beyond anything Japan could overcome or even imagine. Miyazaki requested additional intelligence on American electronics manufacturing from all available sources. What came back over the following weeks was compiled from multiple independent sources. Agent reports from neutral countries where Japanese intelligence maintained networks, captured shipping manifests that listed production figures and factory locations, technical manuals that revealed manufacturing techniques and quality control standards, analysis of serial numbers from captured devices that allowed production volume estimates, and open-source intelligence from American technical journals that published information about factory conversion and production achievements. Each source had limitations and potential for error, but when multiple independent sources confirmed the same basic picture, the conclusions became undeniable. The American proximity fuse production story proved particularly revealing and disturbing. In early 1942, America had produced approximately 200 experimental VT fuses per month. Japanese intelligence had documented this figure and considered it unimpressive. The fuses were still experimental, unreliable, and produced in small numbers. The Japanese assessment seemed reasonable. America was clearly struggling with the technology, just as expected. But by late 1942, American fuse production had reached 2,000 units per month, a tenfold increase in less than a year. Japanese intelligence officers initially suspected these figures were propaganda or included simple practice devices rather than combat-ready phases. But analysis of captured equipment, prisoner interrogations, and agent reports confirmed the numbers. And 1,943 brought even more shocking data. American VT fuse production reached 40,000 units per month, MNA, the rate increasing exponentially as mass production techniques were perfected. Japan, by contrast, had never produced more than 5,000 conventional time fuses monthly, and those represented significant technical achievement. These Japanese figures represented substantial increases over pre-war production and required enormous efforts. Factory expansion, extended shifts, streamlined production methods. Japanese industry was operating at maximum sustainable capacity, and production of 5,000 advanced fuses per month was considered an impressive achievement. Yet the Americans were producing more than 8 VT fuses for every one conventional fuse Japan built, and the gap was widening rather than narrowing. More disturbing still, American production was accelerating while Japanese production struggled under the weight of American bombing campaigns and resource shortages. Electronics production statistics proved even more lopsided and alarming. Japan produced approximately 3,000 radio sets per month in 1943, according to Imperial Navy records. This figure represented a significant increase from previous years, and Japanese leadership celebrated it as proof of industrial strength and mobilization success. The Imperial Navy was being equipped with modern communications equipment in substantial numbers, but American production in 1943 reached 50,000 radio sets per month, more than 15 times Japanese output. When Japanese intelligence officers first encountered these figures, they assumed they were propaganda or included simple civilian designs rather than military-grade equipment. But analysis proved the figures represented combat equipment comparable to Japanese types. In 1944, the disparity widened further. American electronics production reached new heights, while Japanese production, despite intense efforts to increase output, began declining under the impact of Allied bombing and submarine blockade. The Americans were building more electronic equipment in a week than Japan produced in a year. By war's end, the United States would produce millions of electronic devices, including hundreds of thousands of VT fuses, a figure that exceeded even the most optimistic American projections from Ichenjo by Sushira. The sky belonged to the Americans, not because of pilot skill or aircraft quality, though both mattered, but because American factories could build defensive systems faster than Japanese pilots could overcome them, and faster than Japanese factories could develop countermeasures. But perhaps the most devastating comparison involved the manufacturing techniques themselves, because it directly addressed what Japanese strategy depended upon. Japan understood that advanced technology in modern war depended fundamentally on precision manufacturing. If Japan could maintain its traditional advantage in fine craftsmanship and meticulous production, American mass production would be irrelevant for sophisticated devices like proximity fuses. The captured technical manuals shattered this belief system irreversibly. In 1942, Japanese naval leadership had dismissed initial reports of VT fuse development as impossible because they believed miniaturized electronics required craftsman-level precision that mass production techniques could never achieve. The manuals revealed that America had accomplished the seemingly impossible, applying assembly line methods to precision electronics. Rather than having master technicians hand-assemble each delicate fuse, the Americans had broken down the process into dozens of simple steps that could be performed by workers with minimal training. Components were standardized and interchangeable. Testing was automated. Quality control used statistical methods rather than individual inspection. Workers specialized in specific assembly tasks rather than building entire devices. The entire production system had been engineered for volume, while maintaining precision that Japanese experts had insisted was impossible without traditional craftsmanship. These revelations accumulated throughout late 1944 like hammer blows against Japanese strategic planning. Each new piece of intelligence confirmed and amplified the picture of overwhelming American technological superiority. Captain Toshikazu Omai, whose responsibilities focused on naval operations planning, began analyzing American industrial infrastructure through available sources, technical publications, pre-war industrial surveys, open-source information from American newspapers and trade journals. What he found explained how such production was possible, but made the strategic situation even more hopeless for Japan. The fundamental asymmetry was overwhelming. The United States possessed approximately 45% of the world's total industrial capacity, according to pre-war assessments. Japan, even after conquering most of East Asia and exploiting the industrial capacity of Korea, Taiwan, Manchuria, and parts of China, controlled perhaps 5% of global industrial capacity. But crude capacity percentages told only part of the story. American industry was characterized by an ability to shift manufacturing approaches in ways Japanese industry could not match, even when operating at theoretical maximum output. The reasons were structural and systemic, not merely matters of effort or organization. A captured American technical report about VT fuse production proved particularly enlightening for Japanese analysts, trying to understand how American manufacturing achieved such scale. The report, intended for factory managers and production supervisors, described production processes at the Crosley Corporation in Cincinnati. The facility employed 5,000 workers producing VT fuses on assembly lines based directly on radio manufacturing principles. Peak monthly production at this single facility reached 85,000 fuses, with sustained monthly production in the 60,000 to 80,000 range. By comparison, the entire Japanese electronics industry in early 1944, spread across multiple facilities using skilled craftsmen and traditional manufacturing methods, produced approximately 5,000 advanced time fuses per month. Total. One American factory equaled 16 times the output of Japan's entire national fuse production, and this was just one of multiple American electronics production facilities. The report revealed production methods that Japanese industry had never implemented at such scale. Fuses moved down assembly lines just like automobiles. Sub-assemblies were produced in parallel, radio components in one area, battery assemblies in another, metal casings in separate sections, then brought together for final assembly. Workers specialized in specific tasks rather than having craftsmen build entire components. Specialized jigs and fixtures ensured components fit together properly without requiring skilled fitting. Interchangeable parts meant that components could be mass-produced and assembled without individual customization. Quality control used statistical sampling rather than individual inspection of each device. The entire process was optimized for volume production at the expense of flexibility, customization, or craftsmanship. Japanese electronics production, by contrast, retained many characteristics of artisanal manufacturing. Skilled workers fitted components together, making adjustments to ensure proper fit. Tolerances were tighter, finish quality higher, individual craftsmanship more evident. Japanese electronics were in many ways superior products, better designed, more elegant engineering, more sophisticated construction. But Japan produced approximately one conventional fuse for every 16 VT fuses America built. The mathematical reality made quality differences strategically irrelevant. The Japanese discovered that America had multiple electronics production programs running simultaneously at different facilities, operated by companies with different specializations. The VT fuse alone was produced at 5 different facilities operated by electronics companies like Crosley, Westinghouse, and Sylvania, and by consumer goods manufacturers like Eastman Kodak. These companies had no previous military electronics experience but applied their existing manufacturing expertise, TAC, mass production techniques from radio plants, precision assembly from camera makers, quality control methods from consumer electronics, EAS, to military manufacturing with devastating effectiveness. This distributed production model provided resilience that Japanese centralized production could not match. If one VT fuse production facility was bombed or experienced problems, 4 others continued production. Total production barely fluctuated. Japan, with more centralized production, was more vulnerable to disruption. A single successful bombing raid on a critical facility could significantly impact national production. The decentralized American model was not just more productive, but also more resilient, harder to disrupt, and capable of rapid expansion by bringing additional facilities online. Anti-aircraft shell production followed similar patterns of overwhelming American superiority. Japan produced approximately 250,000 anti-aircraft shells of all types in 1943, representing the maximum output Japanese industry could sustain. America produced approximately 5 million 5-inch anti-aircraft shells in the same year, 10 times Japanese output, with an increasing percentage containing the revolutionary VT fuses. Japanese forces in combat noted that American anti-aircraft fire was overwhelming, not because of any technical superiority in the guns themselves. Japanese anti-aircraft guns were often excellent in design, but simply due to volume and effectiveness. American ships fired support missions that consumed more ammunition in hours than Japanese units received in weeks. This was not tactical excellence or better fire control. It was industrial capacity translated directly to battlefield firepower, multiplied by technological breakthrough. Radar technology represented another stark and operationally significant comparison between American and Japanese technological capacity. Modern naval operations require early warning. Ships need to detect approaching aircraft, vessels, and landmarks. Guns must track targets accurately. In short, military effectiveness in modern warfare depends fundamentally on detection capability. And detection capability depends on radar. The Imperial Japanese Navy had developed respectable radar systems by 1943, but they remained in limited supply. A major fleet might have a few radar-equipped vessels. Many destroyers and smaller vessels operated without any radar capability whatsoever. This was not cultural resistance to new technology. It was simple lack of production capacity. Japan produced approximately 100 naval radar sets monthly in 1943, a figure that had to serve both new construction and retrofitting existing vessels. The Imperial Navy never achieved complete radar coverage across its fleet. Many vessels operated with limited or no radar capability throughout the entire war. America produced approximately 1,000 naval radar sets monthly in 1943, almost all for military use. By 1944, virtually every American combat vessel down to small patrol craft carried some form of radar. Every American task force had comprehensive radar coverage, creating integrated defense networks that could detect approaching aircraft at ranges Japanese pilots found shocking. This disparity in detection capability had direct and measurable battlefield consequences that Japanese commanders observed with increasing alarm. American forces could detect approaching Japanese aircraft well beyond visual range, allowing time to coordinate defenses, launch fighters, and prepare anti-aircraft batteries. When American ships detected approaching Japanese aircraft, they maintained tracking through integrated radar networks that delivered targeting data directly to gun directors. The radar-directed fire control, combined with VT fuses, meant that Japanese aircraft were being engaged effectively at ranges, and with accuracy that had been theoretically impossible just 2 years earlier. The technological revolution had rendered conventional air attack obsolete against properly equipped American task forces. A captured American technical report from late 1943 revealed the integration of radar fire control with VT fuses, and this proved particularly devastating to Japanese strategic calculations. The report detailed how radar operators could track approaching aircraft continuously, feeding precise position data to gun directors, which in turn directed 5-inch guns with VT-fused shells. The entire system operated with a level of integration and automation that Japanese technology could not match. Japanese air attacks had become suicidal against such defenses. By early 1945, the mathematical reality of American technological superiority forced the Japanese High Command to consider desperate measures. If conventional attack methods had become ineffective, perhaps unconventional approaches might succeed. The kamikaze strategy emerged not from cultural or spiritual foundations alone, but from cold technical calculation. If aircraft could not survive to deliver bombs on target through conventional attack profiles, perhaps deliberately crashing aircraft into ships might overcome the defensive technological gap. The kamikaze tactic was born of technological desperation rather than pure spiritual devotion. It represented the last hope of overcoming a defensive system that had made conventional attack methods obsolete. The mathematical logic seemed sound. The VT fuse was devastatingly effective against aircraft attempting to deliver bombs and torpedoes through normal attack runs, where evasive maneuvers and approach angles gave the defensive system time to function. But an aircraft diving directly at a ship at maximum speed might overcome the defensive screen through sheer velocity, giving the VT fuses and gun directors minimal time to engage effectively. The human pilot, accepting certain death, would press the attack regardless of defensive fire, theoretically increasing the probability of hitting the target. Initial kamikaze attacks in the Philippines in late 1944 achieved some success, stunning American naval commanders with their unexpected effectiveness. The Japanese High Command interpreted these results as confirmation that they had found a technological countermeasure to American defenses. What they failed to understand was that American naval defense was itself adapting rapidly to this new threat. The VT fuse was undergoing continuous refinement, with sensitivity adjustments specifically calibrated against diving aircraft. Fire control systems were being modified to prioritize kamikaze threats. Defensive formations were evolving to create overlapping fields of fire, specifically designed to counter suicide attacks. Most significantly, American industrial capacity meant that every loss to kamikaze attack was quickly replaced, while Japanese aircraft and trained pilots, SA-self, even those willing to die in suicide attacks, represented irreplaceable assets. The mathematical equation remained unfavorable despite the tactical shift. The captured documents also revealed American electronics research capacity, and this proved particularly devastating to Japanese strategic calculations. Japan had faced chronic shortages of technical expertise since before the war. The nation lacked sufficient numbers of trained electronics engineers and scientists, depending instead on a small cadre of highly trained specialists to develop new technologies. The electronics research program represented a massive national effort, consuming enormous resources and scientific talent to produce incremental improvements in existing technology. Training new engineers required years of education and mentoring. Japanese military operations were perpetually constrained by technical expertise availability. American forces, by contrast, operated with seemingly unlimited technical support. Captured reports showed American research laboratories developing new electronic devices at rates that exceeded Japan's ability to even comprehend the technologies, let alone counter them. Some captured documents referenced entire research divisions with hundreds of scientists working on electronic projects that Japanese forces could barely conceptualize. The waste of technical talent on projects Japanese forces would consider speculative luxuries was routine in American operations. The source of this abundance became clear through intelligence analysis. American universities and technical schools in 1944 graduated approximately 50,000 engineers and scientists annually. Japan produced perhaps 5,000 technical graduates per year, less than 10% of American output. American research laboratories included organizations like MIT's Radiation Laboratory, with over 4,000 scientists and engineers working solely on radar and electronic systems. Japan had no comparable institution within its entire national research establishment. Some captured documents referenced casual collaboration between multiple research laboratories, each larger than Japan's entire electronics research community. Steel production statistics underlined every other production comparison because steel is the foundation of industrial warfare. Weapons, ships, electronics casings, infrastructure, tools, toolamaya, all require steel. Military production in an industrial war is fundamentally constrained by steel availability. Japan produced approximately 7, 8 million tons of steel in 1943, representing maximum output from Japanese industrial capacity plus captured Asian steel production. This figure included output from occupied Korean and Manchurian steel mills operating under Japanese direction. It represented total mobilization of every available steel-producing facility. The United States produced 90 million tons of steel in 1943. America produced more than 11 tons of steel for every 1 ton Japan produced. The combined Allied steel production approached 150 million tons, versus Japanese output of 8 million tons, a 19-to-1 advantage that translated directly to weapons production. More steel meant more ships, more aircraft carriers, more electronics, more of everything required for industrial warfare. The steel production gap was not something that could be overcome through better tactics, superior training, or ideological commitment. It was a fundamental resource constraint that determined maximum possible military production. Japan was fighting a multi-front war spanning the entire Pacific with 1/19 the steel production of its combined enemies. The mathematics of defeat were written in steel production figures. Commander Miyazaki and Captain Omei spent weeks during early 1945 analyzing these figures with increasing desperation, cross-referencing sources, searching for errors or exaggerations that might make the picture less catastrophic. They found none. Every source confirmed the same basic reality. America possessed industrial and technological capacity that made Japanese production look primitive. The analysts prepared a comprehensive report for the Japanese High Command in February 1945. The report was clinical, mathematical, undeniable in its logic. It compared Japanese production capacity to Allied output across every significant category of military equipment, e.a. electronics, radar, ships, aircraft, ammunition, steel. Every comparison told the same story. Japan was outproduced in every category by significant margins, and the gap was widening rather than narrowing as the war continued. But the report went beyond simply presenting production numbers. The analysts included detailed projections of what these production figures meant for military operations over the next 6 to 12 months. They calculated that Allied production advantages meant Japan would face increasing technological superiority in every theater. Japanese forces could continue achieving limited tactical successes through superior training, courage, and sometimes better basic equipment, but they would inevitably lose campaigns through attrition and technological disadvantage. Every ship sunk, every aircraft shot down, every electronic device destroyed would be replaced for the Allies within weeks or months. Japanese losses took much longer to replace, if they were replaced at all. The mathematics of attrition warfare inexorably favored the side with industrial capacity to sustain losses indefinitely, and that side was not Japan. The report included projections for mid-1945 and beyond. If current production trends continued, by mid-1945, Allied forces would achieve both numerical and technological superiority ratios of 10 to 1 or greater in most combat categories. By late 1945, ratios would likely reach 20 to 1 or higher in many categories. Japanese forces, no matter how well trained or tactically proficient, could not sustain combat against such overwhelming odds indefinitely. Quality advantages in individual weapon systems became irrelevant when facing 20 times as many enemy weapons, operating with technological capabilities, an entire generation ahead of Japanese equipment. Even if Japanese forces maintained their tactical skill, even if every pilot and sailor fought to the death, the cumulative losses would eventually destroy the imperial forces through simple attrition. Available manpower was finite, industrial capacity was constrained. Territory was being lost rather than gained, reducing access to resources. The trajectory pointed inexorably toward defeat. The report concluded with mathematical certainty that Japan could not win the war through military means given the current industrial and technological balance. This was not defeatism or political opinion. It was objective analysis based on verified data. The conclusion was professional assessment that should have informed strategic decision-making. The analysts expected the High Command to use this information to develop realistic strategic options. Perhaps Japan could seek diplomatic solutions while still holding significant territory and maintaining some bargaining position. Perhaps resources could be reallocated to focus on defensive operations that might extend the war while seeking political settlement. Perhaps the information could inform decisions about which territories to prioritize holding and which to yield. At minimum, realistic understanding of the situation might prevent wasteful offensive operations that consumed irreplaceable resources without achieving strategic objectives. Commander Miyazaki presented this report to his superiors in the High Command with full knowledge of its controversial implications. He was not a defeatist. His professional record demonstrated commitment to Japanese victory. He was not a traitor. His naval military heritage and personal honor were beyond question. He was a professional intelligence officer presenting accurate analysis so that leadership could make informed decisions. He expected disagreement, perhaps anger at the unwelcome conclusions. What he encountered was something worse: complete rejection of the analysis itself. Military leadership refused to accept the report's conclusions, calling them defeatist propaganda undermining Japanese spirit. They argued that Japanese willpower, superior tactics, and spiritual strength would overcome technological disadvantages. They cited historical examples of smaller forces defeating larger ones through skill and determination: Japanese victories over Russia in 1905, the initial successes against Western powers in 1941–42. They insisted that Allied production figures were exaggerated for propaganda purposes, that American technology was unreliable and would fail in combat, that Japanese spirit would overcome mere machines. Other commanders and leadership figures reacted similarly. They pointed to continuing Japanese tactical successes, to superior Japanese training and discipline, to the defensive advantages of home islands. They argued that Japanese troops were better led, more ideologically motivated than Allied forces. They believed that spiritual excellence could overcome technological disadvantage. Some argued that secret weapons under development, SA, suicide boats, human torpedoes, improved aircraft, would change the strategic balance. Miyazaki attempted to explain that tactics became irrelevant against overwhelming technological superiority, that quality differences disappeared when facing technology that operated on fundamentally different principles, that even the best troops could not fight effectively without comparable equipment, ammunition, and technical capabilities. His arguments were dismissed as defeatism. The report was filed and ignored. The Japanese High Command's rejection of these intelligence assessments represented a fundamental failure to understand how modern technological warfare worked. Military traditions from previous centuries emphasized courage, skill, leadership, tactical brilliance as the decisive factors in warfare. These qualities had won wars for thousands of years. Individual warriors with superior training could defeat larger numbers of inferior opponents. Superior tactics could overcome numerical disadvantages. Brilliant commanders could achieve victory through maneuver and deception, but the Pacific War was different from all previous conflicts. It was the first truly technological total war where victory depended more on laboratory breakthroughs and factory output than battlefield prowess. The nation that could produce more advanced technology and deploy it effectively would win through simple technical superiority, regardless of tactical considerations. Japan's military leadership, trained in traditional methods, could not psychologically accept this new reality. But some Japanese officers did understand. Admiral Isoroku Yamamoto, who had opposed war with America from the beginning based on his understanding of American industrial capacity, had been killed in 1943. But his warnings about American production capability had proven prophetic. Admiral Shigeyoshi Inoue reached similar conclusions after analyzing American naval technology development. He noted in official reports that Japanese technical inferiority meant nothing against enemies who could replace losses immediately, while Japanese units fought with steadily dwindling resources. In 1945, with defeat looming, some Japanese naval officers began advocating for surrender negotiations, recognizing that the war could not be won against American technological supremacy. Their voices were silenced, sometimes through forced retirement, occasionally through more direct means. The official narrative remained one of spiritual victory through sacrifice, regardless of material realities. The intelligence analysts continued their work throughout early 1945, even as their reports were systematically dismissed or ignored. They documented the American invasion of Iwo Jima in February 1945 with the same mathematical precision they had applied to production statistics. The landing involved massive naval gunfire support from ships equipped with radar-directed 5-inch guns firing VT-fused shells. Japanese air attacks against the invasion fleet achieved negligible results despite suicidal determination by the pilots. Of 80 aircraft that attacked the American fleet during the first 2 days of the invasion, 75 were shot down without inflicting significant damage. The statistical analysis was devastating, a 94% loss rate with minimal effect on American operations. The logistics planning and execution involved in such an operation exceeded anything Japan had attempted even at the peak of its power. The technical coordination of naval gunfire, air support, and amphibious operations represented engineering and systems integration capacity that Japanese forces could not match. Each American landing demonstrated increasing technical sophistication. Supply operations established on the captured islands contained more communications equipment than existed in the entire Japanese Navy. Photographic reconnaissance showed radar installations, electronic detection systems, and communications networks covering the captured territory within days of invasion. American combat units deployed electronic equipment at rates Japanese forces could not imagine sustaining. Radar sets were installed not just on ships but on the captured islands themselves, creating integrated defensive networks. Communications operated through encrypted channels resistant to Japanese interception. Electronic navigation aids guided aircraft and ships with precision previously unimaginable. The intelligence services documented American technical superiority with similar precision. By early 1945, American and British technical capabilities had advanced generations beyond Japanese systems. A captured American technical manual from early 1945 described radar systems operating on frequencies the Japanese could not even detect, let alone jam or counter. The American electronic warfare capability alone exceeded Japan's entire signals intelligence establishment. A single American electronic countermeasures unit had more advanced equipment than the entire Japanese Naval Electronics Research Division. Japanese electronics production, despite desperate efforts, peaked at approximately 500 radar sets monthly in early 1944 before declining sharply under the combined effects of Allied bombing, material shortages, and resource constraints. American production in 1945 reached 2,000 radar sets monthly. The Americans were building more electronic equipment in 3 days than Japan produced in a month. The sky belonged to the Allies by 1945 because American factories could build defensive systems faster than Japanese pilots could overcome them. The Imperial Navy was dying through attrition, losing irreplaceable ships, trained sailors, and limited equipment that could not be replenished or replaced. Japanese kamikaze aircraft, like the Oka, represented dedicated suicide technology, but Japan produced fewer than 800 Okas total. They were rendered largely ineffective by the continuously improving American VT fuse and radar direction systems. Quality became irrelevant against overwhelming technological sophistication. The final devastating intelligence came in early 1945 through detailed analysis of Allied technical operations in the Philippines. After the invasion in October 1944, American forces established technical superiority across the archipelago, deploying radar networks, electronic detection systems, and integrated defenses that made Japanese air and naval operations virtually suicidal. For a brief period in late 1944, kamikaze attacks had achieved limited success. This should have created opportunities for Japanese forces to significantly damage American naval assets through continued suicide operations. Instead, the Americans simply upgraded their defensive technology. The intelligence reports documented that American forces were rapidly adapting their VT fuses and fire control systems specifically to counter kamikaze tactics. Analysis of captured technical bulletins showed that American engineers had modified the VT fuse sensitivity to better detect diving aircraft, adjusted radar tracking systems to prioritize high-speed targets, and reorganized fleet defensive formations specifically to counter suicide attacks. Within months, the effectiveness of kamikaze operations declined dramatically as American technical countermeasures were implemented. The analysis was devastating. America had so much technical capability that they could rapidly adapt defensive systems to counter new threats, developing and deploying modifications in weeks that would have taken Japanese engineers years to accomplish. Japan could barely maintain its existing technology. America was continuously evolving its systems in response to battlefield experience. One particular example documented by intelligence analysts illustrated the disparity with painful clarity. The destroyer USS Laffey was attacked by 22 kamikaze aircraft on the 16th of April 1945. Despite being a single ship rather than part of a larger formation, the Laffey's advanced defensive systems shot down 9 attackers. While 6 kamikazes did hit the ship, the Laffey survived, returned to service, and provided data that allowed further improvements to the VT fuse system. Japanese intelligence calculated that the technological defensive capacity of this single destroyer in 1945 exceeded what an entire Japanese destroyer squadron could have achieved with their best equipment. And the Laffey was not exceptional in 1945. It represented standard American destroyer technology, operating with systems that were being continuously improved through combat experience and technical innovation. By mid-1945, the intelligence services were documenting not just American superiority, but the immediate implications of that superiority for Japan's survival. American forces were advancing across the Pacific with massive technological advantages in detection, communications, and defensive systems. American industrial production had recovered from initial Japanese advances and was being accelerated beyond anything Japan had imagined possible. Japanese forces still fought skillfully, still conducted desperate defensive operations, still extracted heavy casualties from attacking forces. But the strategic outcome was never in doubt. The numbers made defeat inevitable. Up next, you've got 2 more standout stories right on your screen. If this one hit the mark, you won't want to pass these up. Just click and check them out. And don't forget to subscribe and turn on the notification bell so you don't miss any upload from us.